Good afternoon to all of you. I, Akash Sharma, on behalf of MIDAS IT, welcome you all to this presentation or webinar on slope stability using the MIDAS solution, that is MIDAS SoilWorks and MIDAS GTS NX. So to start with, MIDAS is having a schedule for the Geotechnical webinar series. So the first webinar topic for today is like slope stability analysis using SRM and LEM. And similarly, we have other 3 webinars scheduled on May 27th, June 10th, and June 24th. With the topics, on May 27th, we have the pile raft foundation analysis with superstructure and substructure. On June 10th, we'll be dealing with the soil structure interaction for shored excavation with using 3D finite element method. And on June 24th, we'll be dealing with tunnel analysis and design using 2D and 3D finite element methods. So for today's webinar, this will be the workflow which I would be performing. First of all, I would be giving a brief introduction about the slope failure, the application where we need to perform the slope stability checks, the method of analysis like LEM, SRM and SAM, the theory behind it, and the categorization of problem, that is 3D and 2D. Then I will give a very brief introduction to SoilWorks and the advantages you have with SoilWorks. Then we'll be solving a problem of plane strain problem. And finally, we'll end with the 3D modeling of using GTS NX and talking about its advantages. So slope failures. Slope failure has recently increased in number considerably with the advancement of infrastructure on or near the slopes, bringing heavy loss to life and property. So what is the solution to slope failures? The solution to slope failures is the proper stability check before one goes for the construction on or near the slopes. Especially some areas where the stability checks becomes very much important are as follows. First is like reinforcement for cut slopes. Whenever you are cutting a slope, the analysis with and without the reinforcement for minimum factor of safety becomes very much important. Also, considering dry and rainy season condition is also very important in this particular case. The second is like reinforced earth retaining walls. So stability check for reinforced earth retaining walls, reflecting various practical reinforcement materials and also considering dry as well as the rainy season condition for slope stability. Next is the slope stability at the tunnel exits. Wherever you have a tunnel exit, slope failure becomes a very important check to perform, and one should perform the check for both the slopes coming onto the tunnel exits. Moving on, next we have the abutment pile foundation of slope. Now with abutment pile foundation, the construction stage analysis becomes very important, reflecting the excavation as well as the backfill. So the effect of pile abutment system could be studied, like what is their influence on the stability of slopes. Now dams or leaves with cutoff wall. Dams are basically a structure in which I think almost all the geotechnical analysis need to be performed, whether it is consolidation, seepage, slope stability. But the important thing with slope stability analysis in dams is that you should be able to consider the pore pressure variation within the dam. While performing the slope stability analysis. So you should be able to perform the seepage slope coupled analysis so that you can consider the variation of pore pressure in the embankment or in the dam while considering the slope stability. So seepage slope coupled analysis becomes very much important. Now let us talk about the various method of analysis available with us. First is the LEM, that is the limit equilibrium method. I think most of you are very much familiar with this method. The next is the SRM, that is the strength reduction method or the finite element method So I'd be dealing with both this method in detail today. So limit equilibrium method. It is a traditional method of analysis based on simple equilibrium condition. Basically in this what we do is that we just divide the failure surface into a number of slices, and the equilibrium of that particular slice is considered about an assumed center of rotation, and then the factor of safety is calculated as follows, like F is equal to SR upon SM, where SR is the overall shear strength of potential failure plane or a pre-existing slip plane, and SM is the total mobilizing shear force acting on per unit area of that plane. Now if you see that particular slice, you will see that there are a lot of forces, the self weight, the interslice forces, similarly the normal reaction from bottom. So there are a lot of forces. Now to consider the equilibrium condition with all the forces, the equation becomes indeterminate in nature. So to make it determinate, there are few assumptions which are need to be made, and this gives rise to the various methods which we divide into simplified as well as the advanced method, like Felenius method, in which the interslice forces, that is X and E, both are considered as 0. Similarly in Bishop simplified method, in which the interslice force, that is horizontal force, that is X, is considered to be 0, and so on. So there are different methods because of this assumption, like Janbu, Spencer, Moxton and Price method. Now the next method is the strength reduction method. It is a finite element method which simulates the actual slope behavior mechanism and determines both, that is the factor of safety and the failure behavior. Now as you can see on your screen, let us consider an embankment. So in strength reduction method, what the program does is that just consider that particular element, let's say A. So the left hand figure is the initial stress condition for that particular element. Now what the program does is that now it goes on reducing the C and phi value, and it reduces till the end the particular element fails according to the Moore circle criteria. So that is the right hand condition. So based on that, the factor of safety is calculated as Fs is equal to tau upon tau F, where tau is the shear strength of the slope material on the basis of Moore column criteria initially, and tau F is basically the failure shear strength of the element or of the material, and calculated as follows. So you can see that tau F is equal to Cf plus sigma n tan phi F, and accordingly the factor of safety is calculated as Fs is equal to tau upon tau F. Now let us see what are the advantages and disadvantages of both the methods. So first we have the limit equilibrium method. It is the most common type of analysis till now. So you could find a lot of research papers and codal provisions for the limit equilibrium method. The analysis time required is very small, and even manual calculation for few surfaces is possible. And it has a very relative ease and transparency in their formulation, so you can just manually check what the program does, and so it gives a user friendliness to this method. The disadvantage of this method is that it involves a lot of assumption regarding the failure plane surfaces and the slice side forces. And also in the post-processing results, the only thing you obtain is the factor of safety, and it can't be used for 3D problems. Now with strength reduction method, all the assumption regarding failure plane surface and slice side forces is removed. Also in the post-processing results, you obtain the stress condition like the displacement, the horizontal displacement, the effective stress condition in the embankment, in addition to the factor of safety. And it is effective both with 2D and 3D problems. Now the disadvantage of strength reduction method is that no well-defined failure surface is obtained, like as in limit equilibrium method, you define the failure surface, so you can say that the soil is going to fail in that particular manner. Also it requires extensive meshing for reliable results, and comparatively the analysis time also becomes high. Now you have seen that in the limit equilibrium method we only obtain the factor of safety, that was the disadvantage, and in strength reduction method what we didn't obtain a clear failure plane surface. So MIDAS products provides with stress analysis method. In this, basically the stress analysis is carried out using the finite element method, and this stress values are used to calculate the factor of safety for failure surface that is assumed in LEM. So it is basically a combination of SRM and LEM, and then the factor of safety is calculated and the critical surface defined with the stress condition in the embankment. Now the categorization of problem. First of all, the problems where one go for 2D modeling, that is we call as the plane strain problems. If the Z dimension of the problem is very large, and it can be assumed that the state existing in the XY plane holds for all the planes parallel to it, displacement of any XY cross section relative to any parallel XY cross section is 0, then you could go for 2D modeling, and such problems are referred to as the plane strain problems. So the method which can be used for the 2D modeling is LEM and SRM, and of course SM, which is basically combination of both. Now the second types of problems is the 3D problem. This is the case when the Z dimension of the problem is not very large, and you can't assume that the state existing in the XY plane holds for all the plane parallel to it. For example, you can see in the figure that there is a wedge kind of thing in the model. So if you consider two different planes, so both will be giving you different factor of safety. So in such kind of cases, you can't go for 2D modeling. And for 3D modeling, the method which can be used is the strength reduction method or the finite element method. So this is basically how we categorize the geotechnical problems whenever it comes for slope stability. So here I would just like to give a brief introduction about the MIDAS product. MIDAS has two solutions. The first is 2D solution, that is for the plane strain problems, called as SoilWorks. SoilWorks is all-in-one 2D finite element analysis and analytical software both for structural and geotechnical engineers. It has its own fully integrated pre and post engine as well as its own solver. It has 7 modules, that is slope, rock, foundation, dynamic, seepage, soft ground and ground, thus covering all the geotechnical problems. So what are the various analysis one could perform with SoilWorks are? First of all, in the ground module, you can perform the static linear as well as the non-linear analysis, as well as you can consider the construction stage analysis. The slope, which is of prime concern for today, we have the SRM, SAM and LEM analysis, as well as you can consider the construction stage analysis, which I would be showing you in detail. In the rock module, you can consider StereoNet and LEM analysis for the slope stability for rocks. In the soft ground, you could consider both the traditional, that is the 1D consolidation analysis, as well as the finite element analysis. In foundation, you could perform the PY non-linear analysis. In seepage, you could consider both the steady state as well as the transient state, and also the coupled analysis. The coupled analysis, I will just talk about it in detail. And finally, in dynamic, you could perform the eigenvalue, response spectrum as well as time history, and also could consider the 1D, 2D equivalent linear analysis. Seepage slope coupled analysis, as I discussed with you earlier, you need two modules, the slope module and the seepage module. Basically what we do in the coupled analysis is that first of all we perform the seepage analysis, let's say on a dam. Then we extract the pore water variation in the dam and then take the pore pressure results to the same model in the slope module. Then we perform the analysis considering the pore pressure variation in the whole embankment. So thus you can consider the pore pressure both in LEM and SRM, and thus could study the effect of the pore pressure on the slope stability, and it becomes very important whenever you are dealing with dams. Similarly, we have the soft ground slope coupled analysis, for which you need the slope and the soft ground module. In this, basically you know that with consolidation there is a settlement in the soil, especially in the clay soil. So with the settlement, how the factor of safety changes or how it affects the slope stability of the embankment could be studied. So for this you need the two modules, that is the slope and the soft ground. So today in the case study, we would be dealing with the plane strain problems. Basically, we would be checking it both with and without the reinforcement, and we would be using both the methods in a single model. So this is one of the advantage of MIDAS SoilWorks, that you could perform all the analysis, that is limit equilibrium, SRM and SEM, in the single case. So basically, as you can see in the figure, there are three soil layers. One would be of landfill layer with the shown properties. Second would be the colluvial layer, and the third will be the weathered soil. So just I will open SoilWorks. Okay. So this is basically the interface of SoilWorks. As soon as you enter the SoilWorks, you need to define the initial parameters. That is basically the unit system, whether it is SI, CGS, FPS, or you can just consider your own unit system for the model. Just click OK and click OK. With MIDAS, SoilWorks has a totally CAD based environment, so all the commands which are used in AutoCAD can directly be used here. So you can see all the commands like command line, arc, rectangle are there. So instead of creating the model in CAD, you can directly create the model here itself. Also, MIDAS provides with the option that, let's suppose if you have created a model in AutoCAD, what you can do is that you can copy it, that is Control C, and directly paste it in SoilWorks, that is Control V. So that is possible. Also, if you have a file, you can directly import it. So let me import the model. So open. So this is the model. So just I will move on to the PPT to make you familiar with the workflow. So the workflow with the SoilWorks is as follows. First of all, you need to do the modeling. That is, you have to create the initial model. Then you need to define the property, that is the ground material property and the structural properties. Then you need to assign these properties, that is the structural and the ground materials property, to the model. Then we perform the meshing, boundary definition, the analysis case generation, performing the analysis, getting the results, and finally the report generation. So this is the basic workflow, so it will be helpful when you start with the model. So after we have created the model, the second step is the property definition. So just go to limit equilibrium method, go to ground material property. So these are basically the model type which are available with SoilWorks, that is more column LEM, elastic ground, and more column. So if you want to consider both LEM and SRM method, you need to take care that which model type you are using. For example, if you are going for strength reduction method, your model type should be more column. And if you are considering the LEM method, the model type should be more column LEM. So you should kindly take care of this fact. Now, SoilWorks provides with a huge database of soil rocks, also with their dynamic characteristics. So, for example, if the particular values doesn't match your local criteria, what you can do is that you can just click it, change the value, and save it. So you can use it for your future model. You need not create the model once, create the material property once again. You just define it, you can just save it, and then you can use it. So for today's model, we would be using the top three properties. and click assign. So you can directly assign it. Now since we are going to perform both the analysis, that is the strength reduction method as well as the LEM method in the same model, we need to define two set of properties, the other set being with the model type of Moore column LEM, that is for LEM method analysis. So just select the layers. Kindly take care that now the model type is Moore column LEM. Click assign. So we have defined the ground material properties. So just close the window. So after that, the second step is defining the structural property. The structural property is basically the property for the nails. So go to limit equilibrium method, and there is in the property, the option is structural property. Just click on structural property. Let the name be nail. Let the element type be embedded truss. Let the horizontal spacing be 2. Section type be rebar. And let us give the area for the stiffness calculation as 0.00624 and click add. So this nail is basically for the SRM method. Once again, while defining the structural property for LEM method, kindly take care of the element type. So let the name be nail LEM, and you can see that below there are different element type like nail LEM, anchor LEM, strip fabric LEM, and strut LEM for definition of structural properties in LEM method analysis. So just consider nail LEM. So let the spacing be 2, 110. Let the tensile force be 115, and rest of the parameters let it be the same. So click add. So close. So having defined the properties, now I would like to show you how easy it is to work with SoilWorks. Let's suppose if you have to now assign the properties. So how do you do it? So let's suppose first of all I need to define the structural property. So what I would be doing is that first I would be completing the modeling and meshing and all for the SRM method. Then I would be doing the property assigning for the second method, that is the LEM method. So let's see how to assign the structural properties. So these curves are basically my nails or the reinforcing materials. So just select the curves. This is the works window in SoilWorks, and whatever property, whatever mesh set is created, you can find it in here along with the loads and boundary condition. So this nail is basically for SRM method, as you can see the name nail, and the second one is nail LEM. So to assign this curve, this property, what you need to do is just drag it and drop it, and it automatically gets assigned. Now in SoilWorks, if you want to assign the soil properties, it is assigned to the surfaces. Now to assign the ground material property, first we need to create surface out of the lines which we have created as model. So just go to geometry, and here we have a smart feature called smart surface, you can see, and as soon as you click smart surface, the surface automatically gets generated. So it is as easy as that. Now to assign the properties, once again, so you can see there is the ground material property. We have 6 property. Top 3 are Moore column LEM. I will just expand it so that you can see it clearly. Moore column, and the lower 3 are basically the LEM method. Now to assign the properties, just select that particular surface and just drag and drop the particular property. So as soon as you see that there is a change in color after you assign the properties. So similarly select the second layer, just drag and drop. Top layer, drag and drop. So this is so simple with SoilWorks to assign the properties to the structural components as well as the ground material property. So after assigning of property, the next thing is with meshing. Now MIDAS SoilWorks provide with the various options like auto mesh, map mesh, grid mesh, seeding, so that you can manually control your meshing as per your requirement. But out of this option, there is an option called Smart Mesh. Smart Mesh is basically one of the other smart feature of SoilWorks, in which basically you just need to define what kind of refinement you require, like very fine, fine, or coarse mesh. Let's say very fine. And for SRM method, it is always recommended to use high order element. So just click OK, check it and just click OK. And the mesh will be automatically generated considering the fineness as well as the coarseness. You can see that it is finer on the region where the nails are there and coarser where it is not required. So it is automatically considered by the program. So this was one of the smart feature. Now after meshing, the next step is the boundary definition. You know that boundary definition with 2D models, it's very easy. But many times what happens, we need to regularly change the model. Let's say the mesh size, the properties. So what we need to do, each time we change something with the model, we need to change the boundary condition. So MIDAS SoilWorks provides with the other smart features that we call as the smart support. So go to load boundary, go to smart support and just write the name, let's say ground support, and click OK. And the support condition is automatically considered by the program. So it is as simple as that. And even in the boundaries, you can see in the boundaries, and you can just right click and go to table, and you can see and you can change any support condition in between if required. It is also, you can directly export it to Excel and you can directly use it in there for your report. So it is as simple as that. So now we have completed the modeling aspect. Now what we'll do is that we'll generate the analysis case. So go to analysis, go to analysis case, click add. So let the first method being SRM without nails. So as I discussed in the case study, that will be considering two cases. One, when there is no reinforcement in the embankment, and the second when we are considering the reinforcement. So use all mesh sets. So these are all the input data which we have created, and this will be the data which will be used in analysis. So we have the colluvial layer, landfill layer, and weathered soil, but we don't want the nail to be activated, so you can just drag and drop it in here. So whatever data you want to activate, just drag it and drop it. So this is the ground support, and self-weight, which is automatically generated by the program, should be activated while for the data which is to be used in the analysis. Now in the analysis control data, you can just control the maximum number of increments and iterations. So just click OK and click apply. So you can see that first case is being generated. Now the second case is with nails. So SRM with nails, just activate the embedded truss and click OK. So we have two cases, one with nails and the other without nails. Now this is how we proceed for the SRM method. Now let us see how we do it for the LEM method if you want to consider it in the same model. So just go to the mesh set and just click uncheck. So it is unchecked right now. Now once again we have to assign the properties. So property assigning is similar to what we did. Just select the curves for the nail and just drag it and drop it. So it's assigned. And similarly for the ground surface layer, sorry, just unselect all, just select, drag and drop. Similarly with what we did with the other method, just drag and drop. So it is as simple as that. It just gets assigned. Now what we need to do is that we need to define the boundary condition, or that is the arc failure condition which is to be used. So just go to the limit equilibrium method, and these are the various ways with which you can define the arc failure surface and ensure the minimum factor of safety for the model. So for this method I am using the arc failure surface. So click on arc failure surface. So let the boundary set name be arc failure. So draw the grid range. Grid range are basically the assumed center of rotation about which the factor of safety will be calculated. So just click on the draw grid range, and you can consider a grid of any size. So it's like a 3-point definition. So first point, second point, and third point. So this is my grid. So always take care that whenever you get the factor of safety at the end, your minimum factor of safety for the assumed center of rotation should be somewhere in between. It shouldn't be at the edges for ensure of the minimum factor of safety. Now I am using the method of using arc radius. So in this, what the program will do is that method of searching the first arc radius. Let us consider any point, let's say this point. So shortest radius is that it will just put a normal, and whatever minimum distance the next curve it goes, it will take that as the shortest radius, and the arc radius increment, let's say I'm giving it 1 meter. So if let's say the first shortest radius was 0.1, then it will go on increasing the arc by let's say 1 meter, like 0.1, then 1.1, then 2.1, and automatically consider the arc failure circles. So the number of arc which you want to consider from 1 point, so let it be 10, and just click OK. So we have just completed the model for LEM method. So for LEM method, we need not define the boundary condition. Basically it is because we just want to directly consider the equilibrium condition. So now we need to define the analysis case. So go to the analysis design, analysis case, add. So let the method be LEM without nails, first one. So analysis method, you can just change it to LEM. Now use all layer sets, but you can see that 0. That 0 is the set for the nails, so we need to deactivate it. And in the boundary set, we just need the arc failure surface, and in the load set, we need to have the load set as the sulfate. Now in the analysis control data, I would like to draw your attention here. The analysis method which you want to consider can be selected from here. So you can see both the simplified as well as the advanced analysis methods are available with SoilWorks. Also, you need to define the slope direction in which it is going to fail, left to right or right to left. So for this particular model, it is right to left. So just click OK. And just click OK. We'll just apply it. So LEM without nails. And the second case, we'll use LEM with nails. So all layer set, that is we have to activate the 0 one also. The arc failure remains the same, and the rest of the analysis control remains the same. So click OK. So just close it. So we have defined the 4 analysis case. Now what we need to do is we need to just analyze and generate the report. So I have just to save time, I have an already analyzed model file. I'll just open it for you. Okay. So now let us see how we get the results. So as you can see that we have generated the 4 cases, that is SRM with nails, SRM without nails, LEM with nails, and LEM without nails. So the factor of safety which we get with the nails is 2.05, and without the nails is 1.375. So, but you can see that in LEM method, what we obtained is only the factor of safety, not any stress condition or any displacement. So I will just show you. I will just have to activate the mesh sets to see the results. So okay, you can see. So first of all, see the displacement in case where there is no reinforcement. So you can find that there is no clear failure surface in the strength reduction method, but you can see that the blue zone is basically the failure surface along with the green surface. So this is how the soil is going to fail. Now after the reinforcement is inserted in the soil, you can say that this zone has been increased, and hence there is increment in the factor of safety. Also you can obtain the various stress condition in the soil. So total stress in XX direction, YY direction for both the cases. Now let's move on to the LEM part. So in the LEM part also you can see that there is increment in the factor of safety after we have inserted the nails. But the results which we obtain is only the factor of safety. So this, you can see that this is how we obtain the result. So you can see that the minimum factor of safety is 1.4266 and it is highlighted in red. So you can just click on it and you can see the failure surface. Now you can see that both the failure surface is pretty much similar to what we got in the SRM method. So I will just show you. You can see that this is the failure surface, and in the SRM method what we obtained was almost the same. That is, the zone of the displacement is very high for this particular case. Now, if you want to do the manual calculation check verification, you can just click on that particular surface and you can see that it is divided into slices. Just double click on the slice and you will see all the values which is being considered by the program for it. So you can just click right side and you can consider each and every slice, the various forces, the tau value, the C value and the phi value which is being considered by the program for the analysis. Also, after you analyze, you get a high quality report automatically generated for your program. So just to show you, I will just open an already report generated file. So you can see that a basic report is automatically generated by the program. So you can see that embankment region, the factor of safety, let's say it is considered as 1.3. So you can change this value in the design options. What are the applied properties which you are going to use? What are the various structural properties you are considering? And what are the various results? So you can see that for this particular case, like the standard safety factor, we have given it as 1.3 and it is coming to as 1.972 and the program says it's okay. So similarly, the various stress condition figures is automatically considered. Now moving back onto the presentation. So the advantages with the SoilWorks. So after you have seen the case study for the plane strain problems, now the different analysis could be performed for the same model. So it helps in checking the model from different aspects and hence ensure the safety for the slope. Second is the construction stage analysis. It helps in simulation of real construction sequence and study the influence of its effects on slope stability. So as I was discussing, like when pile abutment case is there, so you could study its effect considering the construction sequence, that is the excavation and backfilling, and hence becomes very important. Now the third advantage is you can consider the seepage slope coupled analysis. As I was discussing that after performing the seepage analysis, what you can do is that you can extract the pore pressure variation in the embankment and can consider the same for the slope stability analysis, both using LEM and SRM. For this you need two modules of SoilWorks, that is seepage and slope module. The fourth advantage is that you can perform the soft ground slope coupled analysis. That is, after performing the consolidation analysis, you can study the effect of consolidation on slope stability after each stage. So it is very, very helpful to simulate the real ground situations. Now with LEM, composite failure definitions are there. So it helps in ensuring the minimum factor of safety for a particular slope model. As you can see that we have various options like arc failure surface, polygonal failure surface, auto search failure surface, which automatically selects the minimum factor of safety failure plane for the model. In the LEM method for reinforcement definition, you can consider various options which I have already shown you, like nail, pile, anchor, fabric, that is for geogrid, strip and strut. In the analysis method for LEM, we have both the simplified and advanced analysis methods with detailed slice-wise calculation for the manual verification too. So you can see we have the simplified methods like Bishop, Janbu, and also the advanced analysis method like Spencer, Monkston, Price, and Sharma vertical. Also, a high quality report is automatically generated by the program, which could be used by you to directly submit a brief summary of what you did directly to your boss. Now, as we were talking of the categorization of problems, the first was the 2D and the second is the 3D. Now, in the 3D, if the Z direction becomes very large, as I discussed, and it can't be assumed that the state existing in the XY plane holds for all planes parallel to it, you can't go for 2D modeling. So in that case, we need to consider the 3D modeling, and here I would like to introduce you to the product of MIDAS, that is the 3D solution called GTS NX. GTS NX is a 3D finite element analysis software with its own pre and post processor and very effective solver. It has a fully optimized platform for 64-bit, and now with 64-bit platform you can model large scale models and consider multi-frontal meshing for your model. Also with GTS NX you can open 2 to 3 models at a time and hence can work on them simultaneously, just saving your time. So just run the analysis on one model and in the same window you can work on the other model. So it is possible with GTS NX. Now talking about the GTS NX capabilities, so you can see that in the static analysis it has both linear static as well as the non-linear static analysis. Also in the construction stage analysis you can see two highlighted things, that is the stress seepage slope coupled analysis. Basically with MIDAS GTS NX, now you could consider the simultaneous effect of the same. Let's suppose if the seepage is taking place, how it is affecting the stress simultaneously could be studied. So a very real ground simulation is possible, and so is true with the stress seepage fully coupled analysis. In the slope module, you can perform the SRM, that is the strength reduction method, SAM, that is the strength analysis method, and the construction stage considering SRM and SAM method. In the dynamic analysis, you can perform the nonlinear time history analysis, eigenvalue, response spectrum, and linear time history analysis. Now there is an option nonlinear time history plus SRM. Just to discuss in detail, this is basically an analysis case. Let's suppose if there is an earthquake. So what it will do is that it will perform the nonlinear time history analysis and at the same time evaluate the factor of safety using the SRM method, and thus you can check whether an earthquake of a certain magnitude is capable of bringing slope failure for a particular slope or not. So such kind of advanced analysis could be done with GTS NX. Now the advantages with GTS NX, the most important advantage of GTS NX is that you can generate the actual ground surface on your model. We have an option called the TGM, that is the terrain geometry maker, where you can directly import the DXF file and consider the soil variation in your model. Also, let's suppose if you have boring data for let's say 3 or 4 bores nearby and you know what is the depth of each layer for that particular soil, what you can do is that you can just create that DXF file, select that board, and with the help of an option called bedding plane, you will just input the depth of each layer. Now what the program will do is that, let's suppose if you have 3 boreholes, what the program will do is that it will just interpolate the depth of each layer and automatically generate the profile of the soil beneath the soil. So this is how the actual ground simulation is possible. So we have 2 options as discussed. One is TGM. TGM helps in simulating. You can see that in this figure. TGM helps in you creating the top surface profile of the surface, and the other is the bedding plane wizard, which helps you to generate the lower soil or the depth of the soil variation within the soil. Thus you can consider a 3D model very much similar to what is present at the site. Just to show you, Now I'd open a model created in GTS NX. So for such kind of model, you can't go for 2D modeling as you can see that the how the surface is varying. So at any plane you can't consider it as a plane strain problem because it has a varying depth, and even for the top surface and also for the soil layers beneath it. So for such kind of problems one need to go for 3D modeling, and the analysis could be done using the SRM method. So for this model I have considered two cases. So I'll just make you familiar with the interface of the soil of GTS NX2. So this is the geometry, the various options where you could generate your own model, mesh, the material and property, then tabbed wise different analysis method is there. So in the material we have two material property, that is the bedrock. The mode column constitutive model is used for the analysis. So you can see the elastic modulus, the porous values and the non-linear parameters like C and phi values. Similarly, we have defined the weathering soil. So these are the values considered. Now after the analysis, that is after running the SRM method, so let's see how we get the results. Now to show you what are the analysis case we are considering, we are considering two analysis case. That is a dry period, in which basically we are not considering any water table. That is you can see, and we are using the full Newton-Raphson method. So in this we are not considering any water table, and water table definition could be considered in the analysis control. And the other case is the rainy period. The rainy period, basically we are considering a water table to a particular depth. So in the analysis control you can see that it is 1 meter. So if the water table is horizontal, that is most of the case, you can consider it, and if not, what you can do is you can define your own water table as per the variation of the water table using the water level function. So both kind of consideration could be done. Now let us see the results after the analysis. So I will just go to the post-processing mode. So you can see that we have two analysis case result. One is the dry period and other is the rainy period. The rainy period, the factor of safety is coming as 1.00428, which is because of the water table consideration, and the other case it is coming as 1.49821. So with 3D models you can get accurate results for what the actual ground condition is there. Now you can see the various parameters like the horizontal displacement, the stress condition. So to determine in which direction the model is going to fail, you need to consider let's say the Ty displacement. So you can see that this particular region is going to fail first. Similarly, for the rainy season, if you consider so Ty, so you can see that how it is going to fail. So this is how basically we determine the failure surface in case of the SRM method, and in accordance then you can provide the reinforcement, more reinforcement or high dense reinforcement for that particular region. So this is how you can consider even 3D models for your slope stability checks. Now also to show you, in MIDAS GTS NX, you can directly export your model file for your report. Let's suppose I'm considering, let's say the TY translation, and just click OK. And you can see that automatically the model file is automatically considered in the PDF. Now the thing is that whenever we do the finite element analysis, we need to consider a particular view of that model. So working with the model to generate the report becomes very tedious. So what you can do is that you can rotate the model within the PDF itself and just save it for your report generation, which is directly will be in PDF format. Also, if you want to like probe the maximum and minimum value, you could do it. And also if you want to consider any cross section, let's suppose if you are dealing with tunnels and you want to do a particular cross section, just import the model and you can just cross section it here itself in the PDF. So that is possible. So this is how we consider basically the 3D modeling and the slope stability for 3D problems. So moving on to the presentation. So I would just like to summarize what we discussed till today. So the learnings what we learned today are the importance of the different method of analysis, LEM, SRM, SEM, their shortcomings and their effectiveness in various fields. The importance of the semi-coupled analysis, like considering pore pressure, that is the seepage slope analysis, and the consolidation, that is the soft ground slope analysis, and the relative ease in using the MIDAS products to simulate the problem. And also the situation where 3D modeling becomes very important, that is the non-plane strain problems. So with this, I would like to thank you all for joining this webinar. And if you have any queries, you can write to us at techsupport@midasit.com. Also, I'd like to inform you about our upcoming webinars. The next webinar will be on May 27th, in which we'll be discussing about the pile raft foundation analysis with superstructure and substructure. That is basically considering how to give the structural engineer the stiffness for the models after considering the soil structure interaction. Similarly, we have the other two webinars, that is on short excavation and for tunnel analysis. So thank you very much for joining this webinar.